So in today's class, we're practicing and reviewing for your first exam coming up this week, 2 parts. And we're studying right now for the second part, which is on our chapter 3 material, finding derivatives and the different techniques that we had found finding derivatives or tools that we learned to take derivatives. And so right here we have find the value of f of g, the derivative of that composition of function at x equals 4. And so it's actually broken it down for us. They gave us what f of u is, which is cosine of pi u over 12. And they give us that u is equal to g of x, which is 3 square roots of x. And if we looked at the composition of the function, we can do it this way if we want. This is going to equal my f of x function, which is this cosine of this pi 12ths times u. But u in our case is this 3 square roots of x. And so if we rewrite this, we can kind of reduce a little bit that 3 and the 12. 3 goes into 12 4 times. So this is the same thing as pi 4 square roots of x. I'm going to just write it as x to the 1/2 for now. And so now if we want to take the derivative of both sides, we would use our chain rule. The other way that we could have done this, we didn't have to change things. We could have looked at it this way. Recall that dy dx, this was equal to dy du all times du dx. And so we're given here what our y function is in terms of u. And so we could take the derivative of that piece and the derivative of that piece. So the derivative of cosine, that's a negative sign of the inside. So pi u 12ths times, well, we still have to look at this as the chain rule in here. So times the derivative of the inside. So the derivative of pi u 12ths is just pi 12ths. And that's our dy du. Now, if we wanted to look at the derivative of du dx, let's rewrite this as 3x to 1/2. So times the derivative of this. So doing the general power rule, bring down our 3, we get 3/2, and bring down our 1/2 and we get 3/2. X, subtract 1 from our 1/2, we get negative 1/2.
Pi over 2 or pi over 12?
Times the derivative of the inside, so it's pi 12ths. Thank you. Here we need to clean it up. We want this just in terms of x, and so we can go in here and wherever we see this u in here, we can replace with this 3 square roots of x. And so we get, this is negative. I might want to bring that pi, well, let's wait. Okay, so this is negative sine of pi 12ths times u, but u was 3 square roots of x, all times this pi 12ths times 3 all over 2, and I'm going to bring x to the negative 1/2 power down to the denominator, make that positive, and rewrite it as a square root of x. And so let's simplify a little bit in here, and we can do that. I notice again that 3 and that 12, that's going to reduce to a pi 4s. This 3 goes into 12 here 4 times. And notice that we have over here, actually that's not, this is part of the sine function, so I can't reduce that square root of x. And so what I'm left with is this piece in here, which I'm going to multiply together. So pi is in the numerator. I'm going to pull this out front, and I have this negative in here. So I have negative pi all over 4 times 2 square roots of x, which is 8 square roots of x, sine, and we have pi fourths square roots of x. Okay, so we could have done it that way, or we could have done it from this right here after we rewrote what the composition of the function is. And so let's just say that this was y equals. And so if I look at the derivative of this y function, so the derivative of cosine, and I'm going to be using the chain rule. So the derivative of the outer is negative sine of the inner, which is this pi fourths square roots of x, times the derivative of the inner. So if I bring down that 1/2, multiply it times the pi fourths, that gives me pi eighths. X, subtract 1 from my exponent, I get that negative 1/2 power. I'm going to pull that out front, and I'm going to rewrite that x to the negative 1/2 power, bring it down to the denominator and rewrite it as the square root of x. And so I have negative, because of this negative, this pi all over 8 square roots of x sine of pi fourths square roots of x, which is the exact same thing that we got over here. I think it's easier personally that when we rewrote it just as that composition of function instead of breaking it down like they had done for us, and just use the chain rule. But either way is correct. Okay, so the example we have in front of us, and we want to find the derivative of this function, y equals 6 all times secant squared plus tangent x, and then that times the quantity secant x minus tangent x. And so we notice that that's a difference of 2 squares, and so we could just square our first function minus the square of our second function before we even take the derivative. And so this would give us 6 times secant squared x minus tangent squared x. And before I started this problem, I noticed that that was probably going to give us one of our Pythagorean trigonometric identities. And based off of cosine squared plus sine squared equals 1, we could divide everything through by cosine squared and get 1 plus tangent squared equals secant squared. So notice if we subtract tangent squared on both sides, we can see that 1 is equal to secant squared minus x minus tangent squared x, which is exactly what we have right here. And so even before we took the derivative, we have y is equal to 6 all times 1. And now when I take the derivative of a constant, that's just equal to 0. So by going through and expanding that and noticing trig identities had made our life a lot easier. If not, we could have used our product rule there and the derivative of our trigonometric functions, or we could have expanded it like we had done. And then again, take the derivative of this piece. We'd have to use the derivative of trigonometric functions plus the chain rule if we did it that way.
Okay, so if there's a number on the front like that 6, that's multiplied last, right?
Right, yeah, so I would
Alright.
just leave it alone as a coefficient. And then take the derivative and then multiply that result of your derivative by 6.
All right, great. Thank you. Sounds good. And another thing, like normal line is like the line perpendicular, right?
Right, so
Okay,
the
cool.
normal line is going to be the line perpendicular to the tangent line. And so perpendicular to the tangent line. So we could find the derivative of our tangent line. And remember, perpendicular slopes were negative reciprocals of one another.
All right, great, thanks.
So we're given f of x is equal to e raised to the x plus 1 power plus e to the x. And this is all over 1 plus e. And we want to find the derivative of f of x. And this is an example, if you had noticed, which when I first did this, I didn't notice, that we can factor out an e to the x in our numerator. Because we can rewrite our numerator using rules of exponent. Remember, we added our exponents when it was same base and we multiplied. So this e to the x plus 1 is the same thing as e to the x times e plus e to the x all over 1 plus e. And so we could factor out that e to the x in the numerator from both of those terms. And if we factored out that e to the x from both of those terms, notice that we're left with this e plus 1 all over this 1 plus e. Well, e plus 1 and 1 plus e are the same thing. And so those factors actually cancel with one another. And we find that f of x, before we even take the derivative, can be reduced down to e to the x. And so now we've taken the derivative of the e to the x. That's the easiest one to take the derivative of. It's just itself, e to the x. When I had showed it on the video and did it, we ended up getting back the exact same thing that we had started with, which again, if I had noticed and then factored out that e to the x, we would have gotten back e to the x. So if the line 2x minus y equals 1 is tangent to the function f of x equals x squared plus 2x minus 3, what is the point of tangency? Okay, so we are given the line that is tangent to the curve. And so if we're given the line which is tangent, so the tangent line of the curve at some point, and we're trying to find that point, then we can figure out what the slope of our curve is at that value. So let's put this in the form of y equals mx plus b. So we can figure out what the slope of this line is. And so we could, let's add y to both sides and subtract 3 to both sides. And you would get the solving for y that we get y is equal to 2x minus 3. So we can see that the slope of our tangent line is equal to 2. So taking the derivative of our function, that's going to give us the slope at a particular value of our function. And so we want to look at when is the slope of our tangent or slope of our curve f of x equal to 2. So we want to find when f prime of x equals 2. Okay, so let's take the derivative of f of x. And so the derivative of f of x is equal to 2x plus 2. So again, we want to know when is 2x plus 2 equal to 2. And so if we solve for x here, so subtract 2 on both sides, we get 2x equals 0. Divide by 2, we get x is 0. So this is telling me that this is occurring at the value, the point, well, when x is 0, we can find the point. And so we should be able to do it either way, plugging it back into our original function, f of x, or that point is also a point on our tangent line. Well, if I plug back in 0 into my tangent line, I get my y-intercept, which is -3. And if I plug it back in for f of 0, I get just back -3. And so the point of tangency is at 0, -3. So our next example, we have y is equal to 2 all over 5x plus 1 quantity 3, quantity cubed. And then we want to find dy dx. And so we can look at this and we can apply the quotient rule. And then within the quotient rule, when we take the derivative of the denominator, we need the chain rule. We could rewrite this where we bring up that parentheses 5x plus 1 to the numerator and make that exponent positive. So y is the same thing as 2 times parentheses 5x plus 1 raised to the negative 3 power. And so now if we took the derivative of this, it would probably be easier than the quotient rule, and we can just use that chain rule and then rewrite it. And so dy dx is equal to, so bringing our power down front, multiplying it by that coefficient of 2, we get negative 6 of the inside, 5x plus 1, subtract 1 from my exponent, so negative 3 minus 1 is negative 4, times the derivative of the inside. And the derivative of 5x plus 1 is just 5. So let's just rewrite this, and with positive exponent, and multiply that negative 6 times the 5, that gives me a negative 30 on my numerator. And then bringing down to make that exponent positive, we have 5x plus 1 raised to the 4th power in the denominator. So if we did the same example, but instead we didn't see that we could rewrite it.
No, I know what I did wrong.
Oh, you saw. Okay.
Yeah.
Yeah, so you should get the same result using the quotient rule. I even noticed when I looked at this at first, I was thinking about even maybe using logarithmic differentiation and taking the natural log of both sides and rewriting it as a span of logs 2. And then taking the derivative. I don't know, that's probably not easier, but it was one way that I was thinking about it, of doing it. So there's lots of different ways that we can approach these problems, and some ways are easier than others.
Yeah.
Okay, so for our next example, we have y is equal to 2x minus 1 quantity squared. And that's multiplied by the quantity 5x squared minus 6. That quantity is raised to the 5th power. So this is where we would not want to take the time to expand this whole thing out. And so we would use the product rule and the chain rule all together. And so let's look at it where we're taking the derivative of the first function. And so while we do that, again, we're going to use the chain rule. So when we're taking the derivative of this first piece, let's bring down our power down front. So 2 of the inside, 2x minus 1, subtract 1 from our exponent. So we have now just 1 times the derivative of the inside. And so the derivative of my inside, 2x minus 1, is just 2. And that's times my second function, which I'm going to just rewrite it, 5x squared minus 6 raised to the 5th power, plus my first function, which is this 2x minus 1 quantity squared. And then we're multiplying it by the derivative of our second. So bringing our power down front, we have 5 of the inside, which is this 5x squared minus 6. Subtract 1 from my exponent, I get 4 times the derivative of the inside. So derivative of this x squared, 5x squared minus 6 is 10x. So let's clean this up a little bit. I'm going to first, let's just rewrite it. So we have here this 2 times 2. So we really have 4, parentheses 2x minus 1, all times 5x squared minus 6 to the 5th. Plus, I have this 5 times this 10x. So I'm going to write that out here. That is 50x. All times 2x minus 1 quantity squared. And then all times 5x squared minus 6 raised to the 4th power. So we can actually factor and clean this up even more. And so notice that we have these 2x minus 1s. We have one of those in common. And maybe even before we do that, let's look at our coefficient. We have a 4 and a 50. And so we can pull out a 2 from both of those. We can pull out a single 2x minus 1 from both of those. And then if I look at this 5x squared minus 6 to the 5th, there's 4 of those that we have in common that we can pull out. So 5x squared minus 6 raised to the 4th power. So what we have left once we pull that out of this first grouping, well, we need a 2 to make that a 4. We pulled out all the 2x minus 1s, and we need one more 5x squared minus 6 to make that 5 of them. Plus, so we pulled out 2 from the 50, so that's 25. I need my x. We pulled out one of our 2x minus 1s. So we need one left, 2x minus 1. And we pulled out all of our 5x squared minus 6 to the 4th. So we don't need anything left there. So we can clean up what's inside that bracket by distributing and combining like terms if possible. And so we could distribute this 2 inside the parentheses, inside that bracket. So 2 times 5x squared is 10x squared. 2 times negative 6 is minus 12. Let's distribute our 25x to both terms. We get plus 25x times 2x is 50x squared minus 25x. So we're almost there. 2 times the quantity 2x minus 1 times the quantity 5x squared minus 6 to the 4th, all times, well, 10x squared plus 50x squared is 60x squared minus 25x minus 12. So we want to find the derivative of y equals the square root of x times a quantity x plus 2. I notice that I want to rewrite this and then I'm going to have to use a chain rule. And if I just took the derivative of the inside right now, how it's written, I would have to use the product rule. So I prefer not to do that. And so let's rewrite this. So this is the same thing as y equals. Let's distribute that x inside the parentheses. We get the x squared plus 2x. And let's rewrite this to the 1/2 power. And so now it's cleaned up where it's easier to take the derivative. And so now we can take the derivative. So we have dy dx. Let's bring down our power 1/2 of the inside, x squared plus 2x. Subtract 1 from our exponent. So that gives us negative 1/2 times the derivative of the inside. So derivative of x squared plus 2x is 2x plus 2. Okay, so let's rewrite this. We can factor out a 2 from this bracket. And notice when we pull out that 2, it's going to cancel with a 2 in here. And so all we're left in our numerator then is this x plus 1. All over, and so let's bring this down to the denominator and rewrite it as a square root. So we have the square root of x squared plus 2x. And we can leave it like that, or we can pull out the x just like it was written in here. But either way is sufficient. Okay, so we have y is equal to 2x cubed plus 1 quantity cubed all over the cubed root of x squared. And so let's use logarithmic differentiation to help us take the derivative of this. So let's take the natural log of both sides of our equation. So we get the natural log of y is equal to the natural log of this 2x cubed plus 1. That numerator is cubed all over the denominator. And I'm going to rewrite the denominator right now as x to the 2/3 power. So now we're going to use properties of logs to expand this. And the rule of logs is if we have a log of a quotient, it is equal to the log of the numerator. So 2x cubed plus 1 minus, in our case, natural log of the denominator, x to the 2/3 power. And my numerator was quantity cubed. So now I'm going to continue to use my rules of exponents. I know our logs, which means that I can bring my exponent down front. So we can rewrite this as the natural log of y is equal to 3 times this natural log of the inside, 2x cubed plus 1, minus, bringing my exponent down, 2/3 natural log of x. Okay, so let's now take the derivative of both sides of our equation. And so remember, when we take the derivative with respect to of y, y is a function of x, and so we have to use that chain rule and multiply by dy dx. So the derivative of the natural log of y is 1 over y times dy dx. This is equal to, I can just leave the 3 alone. Derivatives of natural logs is 1 over what you're taking the natural log of, which is 2x cubed plus 1 in this case, times the derivative of the inside. So derivative of 2x cubed plus 1 is 6x squared. Minus, so 2/3, and derivative of natural log of x is 1 over x times the derivative of x, which is 1. Let's see if we can clean this up a little bit. So we have 1 over y dy dx is equal to, well, 3 times 6x squared is 18x squared, all over our 2x cubed plus 1, minus 2/3, minus 2/3, or 2 over 3x. Multiply both sides by your y to get dy dx by itself. And so we get dy dx is equal to y, but y is what we originally started with, right? So when we write y on this one side, because those cancel on the left-hand side, we're going to write that y as this 2x cubed plus 1 cubed all over the cubed root of x squared times this whole side, 18x squared all over 2x cubed plus 1 minus 2 over 3x.